And so let's see. Now I want to try to bring up the notes. Hopefully this works. I want to say it's this one. Yep. All right. Okay, can everybody see that pretty well? One drawback for today is you're going to have to be able to read my handwriting on my paper notes. So hopefully this works out okay. And everybody should have a copy of the notes, otherwise they were in the front of the room. So like I said, the reason why I wanted to go over it like this today is just because, you know, this is a pretty heavy packet. And if we had gone through this, you know, if we actually went through this in detail and actually wrote this out using the graphics tablet, this is about 5 hours. So, you know, for those of you who want to get out of here by 7 o'clock, this is pretty much the only way to do it. And also, when I do teach the electrodynamics class, I basically go through all of the notes like this. And the reason why is because all of the notes are like this in the electrodynamics class. So take that how you will. But the nice thing about this is that you're going to see a level of detail in what I'm going to explain here that I don't normally, or not normally able to get into when I'm teaching the notes of the graphics tablet. So the idea here is that to talk about special functions. And the way I'm going to get to the special functions is by is essentially through separation of variables. And where I'm going to get this from is actually from the book by J.D. Jackson, not from either Arfin and Weber or Matthews and Walker. So this is the one lecture I'm going to get out of a completely different book than the required books for this class. Although everything I'm going to go over is going to be very relevant for that. And so that's why I call this boundary value problems in electrostatics, because this is exactly the same lecture I used to give in the E&M class. So if you want to follow where this is, if you go to J.D. Jackson's book, look in chapter 3, and basically it's 3.1 through 3.8. So the idea here is that you start off with Laplace's equation and you write this in spherical coordinates. You can see it looks something like this, where what happens is we've done just like we did last week, where we take the potential and we're going to separate the potential into part of it that depends on R, part of it depends on theta, and part of it depends on phi. So this is exactly the same as the expression we had last week with Laplace's equation in spherical coordinates. So then, when you apply your separation of your new variables, then you could just throw those into the overall equation and then just divide out this phi term. And the result is going to be that you'll end up with some of these terms where they only depend on R or theta or phi. And so, for example, here, you could see that the phi terms only exist in the last term here. And so if you divide out the theta and the R terms, then there's only phi here. And so it becomes possible to kind of separate that out and treat it like a constant because it doesn't affect anything else. And so what happens right here is they multiply everything by the R squared sine theta, and you end up with a term here that only depends on R. You have a term here which depends on theta, and there's like one little R term involved. And then this last term only depends on phi. And so we take the phi term and we say, well, that's equal to a constant. And we say that constant is equal to minus m squared. And then, so the solution to the differential equation that it solves is just Q is equal to e to the plus or minus Im phi. Okay? Same as last week. So now we take that constant and we plug it in to the other equation. And we also, at the same time, we assumed that the theta terms, since they were isolated, only depended on a constant. So we threw in another constant, L times L plus 1. And what we got is that we reduced the entire theta term to just depend on constants, and we had a different equation for the R terms, which only depended on the constant. And the solution for the R terms is just this A times R to the L plus 1 plus B times R to the minus L. And meanwhile, the theta term formed a differential equation which can be solved by this associated Legendre function. Because this is the generalized Legendre equation, just like we talked about last week. And so when you put all this together, this forms the solution to the potential in spherical coordinates. So what I want to do mostly now is to say that, well, this is where, as physicists, we come up with an idea of this special function called the associated Legendre function. And so I wanted to go a little bit more into what is this function and what does it actually mean. This is the math methods course. So this is the Legendre differential equation. We're not going to invent this. This has already been invented. We just need to understand it and know how to use it. So this, obviously, some guy named Legendre found the solution to this equation and put it together. And you'll notice here that if you assume that x goes from -1 to +1, then you can use a power series like we talked about earlier in the semester, and you can expand it around x equals 0 and find a solution to this differential equation. So in other words, you're just assuming a power series solution and that you have a solution in the range of the magnitude of x is less than 1. If you do that, then if you take x to any power, it's always going to be less than 1 or even infinite powers, or maybe even go to 0. And so you can have this power series that actually makes sense. And so this is the whole idea behind how the solution to this thing works. So if you take your infinite series here and you sub it into the differential equation, and then you look at all the like powers of x and just equate all of them, then you can see that you have this relationship between C2 and C0 and C1 and C3, and then all the higher order terms, C4 and C5, could be written in terms of C0 and C1. And so if you know what C0 and C1 are, then you know your solution. Now, here's the thing. See, if x is equal to 0, then your solution is just C0. If x is equal, if you take the derivative of this whole function and then take x equal to 0, then you can get your C1. So in other words, if you know what your solution and its first derivative are at x equals 0, then you know what C1 and C0 are, and then you know what all the coefficients are going to be. So in general, for the higher order terms, C of I plus 2 divided by C of I comes from this funky relationship between all of these chosen values of I and N and whatever. Where N, remember, it comes from Legendre's equation up here. And so you can actually write your solution to this differential equation by just kind of plugging in what all these coefficients are in terms of C1 and C0 and your chosen values of N. And so this looks really ugly, but you can continue simplifying this. You can sum up the C0 terms, and right, this is a summation, and the C1 terms in terms of summation. You can see that this works based on the patterns you saw before. And you'll notice that these two terms look somewhat alike. I mean, the only real difference here is that here you've got a 2k plus 1, here you just have a 2k. So it's almost like these terms are all odd, and these terms are all even. And so you'll notice here that if you have an even value of n, then the first series is going to be a polynomial, which is this polynomial here, which is C0 times this stuff. And they simplified it a little bit by taking r equal to n over 2 minus k. And of course, n is even, so that means that this is an integer. Now for odd n, the second series becomes a polynomial, where you're basically, it looks almost the same, except for now you have r defined by n minus 1 over 2 minus k, which works if n is equal to an odd number, then that's still an integer. And so what you get is that for any value of n, you're going to get a polynomial, and the polynomial is going to look something like this, where they've kind of thrown in this arbitrary coefficient in front, which takes the place of the C1 or C0, and and some of the other terms that depend directly on n that are in here. And so you could see that this is the solution of Legendre's equation, and it is an infinite series. And that's kind of where it comes from. So now you have this polynomial, and you could see that it's written here as an infinite series, and you can also write it here as an infinite series but using derivatives, where you're taking the nth derivative of these x terms in order to kind of recover some of the terms in the infinite series. So it's an infinite series, but it's just using all this other stuff. Now you can take the derivative and you can pull it outside of the summation, like we did here, and then you have something a little bit simpler. And another way of writing it is that they were actually able to eliminate this series by, I think they were able to argue it was like a geometric series or something. Or I can't remember if it's a geometric series, a familiar series, or what. But once you pull the derivative outside, then you could argue that this whole series was just equivalent to x squared minus 2 to the nth power. And so you've kind of eliminated the series, and now you just have it as a derivative. So this is really interesting because we basically have now this solution to this complicated differential equation, and we can express it as an infinite series, or we can express it as an nth derivative of something. And what they do typically is they'll normalize this so that if you put 1 in instead of x, then whatever the polynomial is should become 1 for every possible value of n, which makes a lot of sense because you can see here that if you set x equal to 1, then that ends up turning into 0. But you can kind of see how in this summation, if you say x is equal to 1, then you're just dealing with these n's and r's, and you can make that somehow to be equal to 1. So the idea is that you're taking the derivative and then you set this thing equal to 1, and it works. And so one way to think about it is that with this nth derivative term, you've got x squared minus 1 to the nth power. And you can break that out as to n x minus 1 terms and n x plus 1 terms. And you're taking the nth derivative of it. And what will happen is when you're taking the derivative, you're taking the chain rule. So you're taking n derivatives, so you could take n derivatives of the x minus 1 terms and be left with the x plus 1 terms. Or you can take derivatives of the x plus 1 terms and leave the x minus 1 terms, or some combination of the two. But what happens is, if you take derivatives of all the x minus 1 terms, then you're just left with 1 here when the derivative is eliminated. And then you just have x plus 1, x plus 1, x plus 1 all multiplied together. Set them equal to x equals 1, and you've got 2 times 2 times 2, so that's 2 to the nth power. Right? And so to normalize this, what you can do is there's n factorial different ways that you can end up getting this 2 to the nth power. And so you can apply the derivative, set x equal to 1, and get this term, which you could see the n factorials cancel out, and you just have 2n times k to the nth power. And you can normalize it where you take kn equal to 1 over 2n. So this is the normalization, and then when you apply the normalization, then this becomes your Legendre function, or Legendre polynomial, where you could see that this is given by Rodriguez formula, where it's just an nth derivative. Okay. And the normal way that you'll see these being expressed is the P0 term of the Legendre polynomial is just 1. The P1 term is x. P2 is going to be this some term involving x squared. P3 is going to involve x cubed as the highest term. P4, so on and so on. So that's why they call it a polynomial, because you can see that you get these higher and higher order terms. So this is the way that you may have seen Legendre polynomials in the past. Does it look familiar? Okay. So, and this is kind of just a really, really brief where this thing came from. And I think it's good to know it because first off, it just provides a good example of how you can solve this really ugly differential equation and get it into something analytic you can work with. And secondly, you can see here that this allows you to get to the definition you commonly see of a Legendre polynomial. Now, there's also what they call a contour integration representation of this, where from Cauchy's formula, you know that you could write f of z as equal to this integral over a closed contour of f of t divided by t minus z, assuming that f of t is an analytic function. So so then if you take the nth derivative of this, then you get this other function that we already know from contour integration. And you've proven that this is true in your homework. So what they did was they said, well, what if you assume that this representation, this derivative representation of the Legendre function is an analytic function, and so you plug it in to this integral, and then what pops out is just going to be the Legendre function. So this t squared term here, you have this nth derivative coming about because of the nth derivative that we see up here. And then we have the analytic part, which is the t squared minus 1. And you have the 1 over 2 to the nth power, which is a normalization constant. And so we plug this in, and this is known as the, I'm going to mess this up, Schläfli's integral representation. And So what happens then is if you take, this should literally be the same thing as the as what we saw for the Legendre polynomial. So now what you can do is, if you take t equal to z plus square root of z squared minus 1 e to the I phi, where phi goes from 0 to infinity, 0 to 2 pi, then this term in the numerator inside the integral can be rewritten as this term involving t minus z and z plus square root of z squared minus 1 times cosine phi, and the dt can be written in terms of t and z and d phi. And you can see where this is coming from. They're basically rewriting this so that t can be expressed in complex variables, and where it still has a singularity at t equals z. So when they express all this, they can write the Legendre polynomial now in terms of the z and basically eliminate the t. And this is known as Laplace's integral representation. So there's two different ways of expressing the Legendre polynomial as an integral. So, any questions so far? Yeah.
Is that z squared minus 1 in the square side?
No, this is z squared.
Okay.
Yeah, z squared minus 1. I guess if it was 2 squared minus 1, I'd just say it's 3. Any other questions?
One you said we got to prove in our homework. Is that a homework problem?
That was one I think I already gave you, didn't I? Or I did it. I think I did it either homework or recitation, where we actually proved that this relationship was true. Yeah.
I think it was one problem where you sort of proved it logically, like prove it for n.
Yeah. Yeah. Yeah, because I mean, basically, we prove it that must be true if this is true or something like that, by just taking derivatives of the thing. But anyway, this is just one of the interesting things about these special functions like the Legendre polynomials, just the idea that you can express it in different ways. And then this brings us to the idea of the generating function. And so here, what we can do is if we do a summation of a Legendre polynomial with some other term we're going to call h to the n, then that creates this analytic function f of h and z, where if you take this Laplace's representation here, and you literally do that, where you take the integral and you multiply this by h to the n, and then you sum it from n equals 0 to infinity, then this is what naturally comes out, where you can see you have a summation inside the integral because they commute with each other. And when you look at this, this actually looks like a geometric series, right? Because you have h to the n, and then you have this stuff involving the z's to the nth power. So if this is a geometric series, then you know the solution to it, which is this. And so you can literally solve that and turn this ugly thing involving the nth power into an analytic function, which you can now integrate. And when you integrate it, what you're left with is that f of h and z is just this 1 over square root of this stuff. Or just a 2hz plus h squared term in here. And so these generating functions are really interesting because they're basically much more nicer, compact analytic functions that you can use that can kind of sneak in all the properties and all the special stuff about the Legendre polynomial. You know, it's kind of like just a way of kind of packing things up so that you can deal with it later. And so if you use this whole 1 over magnitude x minus x prime is equal to this thing in terms of r squared plus r prime squared minus 2r r prime cosine theta, which is something that you'll see in electrodynamics if you haven't seen it already. Then you can pull out the r and you get something which looks a lot like the generating function, the analytic representation of it. And so all you have to do is assume that h is like r prime over r and z is cosine of theta, in which case this looks just like the generating function. And so you can say then that this 1 over magnitude x minus x prime can be rewritten in terms of r prime over r to the L powers, and then your Legendre function. And this is what you see in electrodynamics all the time as basically the, it's essentially the Green's function for spherical coordinates, which is also in electrodynamics something you're always going to use this 1 over r, or 1 over x minus x prime magnitude a lot. And so this is the spherical coordinate equivalent of that, where it assumes spherical coordinates with azimuthal symmetry, so there's no phi dependence. And the way this is often written in the text is that it looks at r and r prime, and it says whichever is smaller, r or r prime, gets the less than, the other one gets the greater than. And you can actually rewrite your 1 over r in spherical coordinates using Legendre polynomials. So this generating function is useful because it can also, if you take the derivative of the generating function with respect to h, then you get the generating function times a bunch of other stuff involving h and z. And you'll notice here that if you take the derivative of the generating function with respect to h, multiply it by some stuff involving h and z, you get back the original generating function multiplied by some function of z and h. So if it works for the generating function, that has to say something about the polynomial. And so if you substitute in the polynomial and you equate like values of h to the n, what you get is this thing, which is going to relate different n values of your Legendre polynomial to each other. And you can see that here it's a little bit simplified. So you have p to the n plus 1, p to the n, and p to the n minus 1. And they're all kind of related to each other by these multiplications. And this is called a recursion relationship because it allows you analytically to move from one Legendre polynomial to the next, and with just being able to change a parameter. You also notice here that if you do the same thing but you take a derivative with respect to z as opposed to h, you get another function, which leads to a different recursion relationship involving derivatives of your Legendre polynomial. Okay? Now this is really big, and let me tell you why. The thing that's big about this is it's saying that we can calculate the derivative of a Legendre polynomial exactly by just knowing the values of the Legendre polynomials with other n values or whatever. So we can get other, we can calculate its derivative exactly. We can go from one value to another just simply by just knowing what the other values are and just putting in the terms. Now, this is really useful if you're talking about like numerical methods, because one of the big problems in computational physics, the big problem is a simple problem, is how do you calculate a derivative? Because, if you go back to your calculus class a long time ago, you calculated derivative by basically taking the difference between the solution at one point and a solution at another point divided by how far apart they are. But the problem with that is that when you have a finite grid, you're always making a finite error every time you do that. And your errors add up over time, and so you're not getting an exact solution. So one way that people found around that was if you can assume that your system is an analytic function like e to the I theta or e to the I kx, then you know that your derivative is exactly ik times e to the I kx, and you know your derivative everywhere from calculating that. That only works, though, if you have a periodic system. With your Legendre polynomials, what this is saying is if you have a system which can be solved with the Legendre polynomials, you can exactly calculate their derivatives using the same technique. So this is how one of the ways that we might be applying this in physics is that we can use these recursion relationships in order to exactly calculate what our derivative should be without physically going through and having to take this finite differencing and dealing with all the errors that pop out. And this is a technique that's used in a lot of engineering, it's used in physics, it's used in pretty much anything dealing with computation. Do you have any questions on this? This is not the most difficult thing you guys have studied in here, but it is one of these topics that's sort of long as far as how much material is covered. All right, so we can also evaluate this function, and so this is p sub n of z at certain points. And what we do is we can take advantage of the normalization that p of 1 is equal to 1 and rewrite the generating function where the generating function ends up just like h to the n, which is a geometric series, which we know is just 1 over 1 minus h. And that gives us the series, and that kind of verifies that this normalization must be true. We also, a very interesting fact about these is that they're orthogonal functions. And you can see that if you take two Legendre polynomials and you integrate them from -1 to +1, since x has to go from -1 to +1, and then what happens is you can reduce both of these to their difference form. And then you do integration by parts. And then you do integration by parts again and again and again. And eventually what you'll get to is you have the m plus 1 derivative of one part and then no derivatives of the other part. So what happens is that if m and n are different, then what happens is when you take m plus n derivatives of the m term and m is less than n, you're going to get 0. Because you've taken all the derivatives of each one of these and then you just run out of terms. But if m and n are equal to each other, then what happens is you take all the derivatives of this for m. Remember there's two m terms here. And so you're taking 2m derivatives, and you're getting a non-zero term, and then you still have this integral left. And so you can see here that if you take m equal to n, you do the same thing when you do your integration by parts again and again and again, and then you're left with this thing, which just simply involves the integral from -1 to +1 of 1 minus x squared to the nth power. And we can actually solve that by making a clever substitution here. And you can see that the end result ends up being something in terms of gamma functions. Where it's gamma r times gamma s divided by gamma r plus s. Times this other stuff involving the normalization. So what we get from that is that the Legendre polynomials are orthogonal functions, just like sines and cosines. So that means that everything we did with Fourier transforms and stuff like that, and everything that we talked about with the eigenvalue problems, you can use all of that here. And since these functions are orthogonal, any function f of x, which you can range x from -1 to +1, could be expanded as a series of Legendre polynomials. So what you can do is you just set up your x in such a way that it goes from -1 to +1, and this works. You can have your x equal to cosine theta, for example, and cosine theta goes from -1 to +1, and it works. Okay. And since you can do that, then you can take each one of these and assume they're like an eigen function, because they're all orthogonal to each other, and you can expand the space of all the possible solutions that fit into that, multiply them by coefficients, and you get some function f of x, which solves your problem for those same boundary conditions. And then if you want to take your derivative of your function, well, you can find the derivatives by using the recursion relationships, and then you know all your derivatives of your function. And you can find the coefficients by just integrating it with the function, just like you normally did with it, and throwing in a normalization factor. All right. I know I'm throwing a lot out, so if you guys, if this gets confusing or something like that, just ask a question, okay? So the basic idea here of special functions so far is just understanding that what you can do with them is what I really want you to take away from this. I'm not expecting you guys to be able to derive the Legendre polynomials from scratch on a test or anything like that. I just want you to be able to know, understand the generating functions and how those work, understand kind of roughly where these solutions came from, understand that these are orthogonal functions, and that, as such, you can do things like this with them. All right, so there's also a second linearly independent solution to Legendre's equation, and that is if you throw in something like y equal to v times the Legendre polynomial, and you throw that into Legendre's equation, then you can see that you're going to get a slightly different differential equation, where you have v prime and v double prime here. So what you can see here is that in solving this differential equation, you can come up with a solution where v is equal to taking some constant times the integral of 1 over 1 plus x squared times your Legendre polynomial squared. And so the solution that comes out of this is going to be this thing called Q of Z, where Q of Z is effectively a second solution to your problem here. And you can see this comes from integrating this guy from infinity back to Z. And so you can see here, Q is your Legendre function, and then you're just multiplying it by this natural log of Z plus 1 over Z minus 1. And then we're assuming that there could be this other function, f of n minus 1z, where this is a polynomial of a degree n minus 1 that also responds to z. Now, if you want this q to be a single value function, then x has to only range from minus 1 to plus 1, and z has to be greater than 1. Otherwise, you run into problems with z here. And so we can rewrite this second solution by just simply taking your x value and just perturbing it a little bit. And you can see you end up with something like this. And then you take these two and you average them on both sides of the solution, and we see that we have essentially your Legendre polynomial times the natural log of 1 plus x over 1 minus x. And then this other term ends up going to 0 as z to the minus n plus 1. So this other term sort of disappears as we go, as you get larger and larger. So this leads us to this thing called the associated Legendre function, where in our original separation of variables, we had this m term, and if you look back at the notes, we kind of neglected this m term when we were doing all the rest of the stuff for the Legendre's equation. And so if we bring this back, what happens is you end up with another solution where your solution, instead of it being y, it's going to be 1 minus x squared to the m over 2 times the m derivative with respect to x of y. And so that literally just modifies your Legendre solution to where it's the m derivative of the Legendre solution and then this other term multiplying it. And this is known as the associated Legendre function. So you can also do the same thing with that second solution of Legendre's equation, where your q becomes a q, instead of just being qnx, it becomes a qnmx. But what happens with the second solution is if you take x equal to 1, then you have right here x equal 1, and you end up getting something singular because x doesn't actually go all the way to 1 in the second solution. So we have these associated Legendre functions that we have in addition to the regular Legendre function. And you can see that these things are orthogonal, just like the Legendre functions were, where if you integrate from minus 1 to plus 1, that you end up with something times the delta function. And also, since they're orthogonal, you can expand out an arbitrary function in terms of them, because they're essentially eigenfunctions. And you can also use this to express the solution to a problem. Where what's happened here is we're saying that if you have some function of solid angle, that you can expand it out in terms of some coefficients times associated Legendre functions as a function of cosine theta, and then this e to the I m phi. And unlike the previous one, this does not assume azimuthal symmetry. And so what this is saying then, and this is a really strong statement, any problem that you have in spherical coordinates can be solved with this, taking care of the angular part. So if you run into any kind of problem where it has a spherical, it's a spherical problem in electrodynamics or quantum mechanics or anything, it's basically going to come down to this for the angular part. And then the only question is, how do you deal with the radial part? And so you can get like atomic orbitals, you can get the motion of charged particles around a central potential. You can use this to describe the motion of planets around the sun and the gravitational potential. Pretty much anything that reduces spherical coordinates. Okay. All right, any questions so far? All right. So this takes us to spherical harmonics. And the idea of spherical harmonics is that these are essentially the associated Legendre polynomial solutions that you have, only we've kind of added some extra stuff in here to normalize them. So that now you have your associated Legendre function, and you can see here that there's either plus one or minus 1 to the m, depending on whether m is positive or negative. And you could see that this is written here in terms of the associated Legendre function. This is it written in terms of the derivatives representation of that. And you'll notice that these spherical harmonics, which you've probably seen a lot in your physics books, it's just a more compact way of kind of expressing these solutions that are have this angular dependence. And then for all values of m, what you'll see is that there's this relationship between plus m and minus m, like this. M, as you might recall, has a range from minus L to L, where L can go from 0 to infinity. You can also see that these spherical harmonics are orthogonal to each other. So they obey the orthogonality condition, which means that they can function as eigenfunctions, and then you can sum up any solution you want in terms of these things. And so this is the coefficient BLM, which you find by just simply integrating your function with the spherical harmonics.
Is L related to the angular momentum? In quantum mechanics, you have m that's representing
Spin? Yeah, exactly. And you're exactly right. What's happening in quantum mechanics, L here represents the angular momentum number. In quantum mechanics, we call these quantum numbers. So this would represent the angular momentum, and then that could represent the spin. In electrodynamics, L could represent the multipole number. And so it's really funny because you're really seeing the exact same physics. It's just expressed in different ways. In classical mechanics, you can also use this if you're doing like orbital dynamics or something. But it's a very powerful thing because it's all it's really doing is just making a statement about your spherical problem. And if you're solving like a hydrogen atom, you're going to be doing something like this in spherical coordinates. All right, so there's the addition theorem in spherical harmonics, where basically you're taking advantage here of the fact that these things are orthogonal, and that when you do a summation of the two, this is effectively a delta function. And so then you can go from f of theta prime to f of theta. And you'll notice here that if you say that the difference between these two solid angles is some angle gamma, you can express gamma in terms of theta and phi, like this. And then the delta between the two angles is equal to the sum of Legendre polynomials between the two angles, because this is literally just some arbitrary function that is created by summing up all these eigen functions of angle. And then you could find your coefficient by just simply integrating this. But when you do your integral, you of course have a delta function here. And so you're going to end up with just the p of 1, which is normalized down to 1, and so you have 2l plus 1 over 4 pi. And so this is your coefficient that will get you from your solid angles orthogonality to your Legendre polynomial. And so what this is saying is that if the coordinate axes are rotated arbitrarily, any spherical harmonic is a linear combination of YLM prime of the new coordinate omega bar with the same L. And so what you end up with is saying that you can take any spherical harmonic and you can rotate it to give you another spherical harmonic. So they're like eigen functions, but they are when they're orthogonal to each other, but they're really geometrically orthogonal. Is what this is saying. And so you can write your spherical harmonics as combinations of other spherical harmonics, because all they really are just different rotations. And so if you take m equal to 0, then your spherical harmonics just reduce down to Legendre polynomials, like this, with, of course, this normalization in front. And you could see here that you could say, well, in terms of this gamma angle, your spherical, your Legendre polynomial is just this other spherical harmonic at a different angle. And that if you sum over all of these Legendre polynomials, you'll get back this guy. And so what you're really doing here is you're really just adding up different angles. And so when you can see here, when they put the two Legendre, or these two spherical harmonics together, that was effectively just summing over these Legendre polynomials of all these different angles. And so this gives us a way to sort of add up angles within the spherical harmonics and make everything consistent. And so this is the way that the spherical harmonics are normally represented in the text. And you can see here that, you know, with the 0, 0 term, it's just essentially a constant. And then for the other terms, you'll have like sines or cosines, and then you have them to different powers, and then you have the e to the I phi terms as well. And so these can be used to construct all these solutions in quantum mechanics, you guys know. All right. All right, so how's everybody doing? You need a break? Yeah. Because right now we're at the natural break point, because the next thing we're going to do is we're going to get into Bessel functions, which are very similar to Legendre polynomials. And so if you guys need a break to stay sharp, I think this might be a good time to take one. All right, so we'll give you about 5 minutes, and then we'll meet back here. Okay, so now we'll switch gears and we're going to get into Bessel functions. And so Bessel functions are a little bit simpler than Legendre polynomials, and I like to cover the Legendre polynomials first just because once you've seen those, this is just going to kind of reinforce everything else you've seen in a simpler way. So we start off again with the Laplace equation, and this time we're in cylindrical coordinates. And so you can see that there's a z² term and the rho terms as opposed to r, theta, and phi. And so you do your separation of variables in terms of rho, phi, and z. And you plug that into the original equation, and then you and divide through. And what happens is, like, the z equation divides out really fast and cleanly. And so does the theta equation. And so what happens is you could see that we kind of threw in these constants in order to make this work. And then the r equation ends up just being a function of rho, and then you can see the two constants, the k² and the v². Now, for the z equation, since this is a negative term, it's solved by an exponential e to the plus or minus kz. So it's an exponential term which either increases or decreases with z. It doesn't oscillate. And then the phi term, since it has the plus v squared, it actually is solved by e to the I v phi. And so that one actually changes and oscillates. And you'll also notice here that, so these two equations are already solved. That's 2 out of 3 down. The last equation for r, you can solve it using a parallel to the Bessel's equation, where if you take x equal to k rho, you can see that you have this equation, which looks a lot like Bessel's equation. You know, I think the only difference is we just got to multiply here by x² and it's the same thing. And so to solve Bessel's equation, we do the same thing we did before, and that we just assume an infinite series solution, like we did with the Legendre polynomial. And when we do that, we can equate like terms, and we see that certain things fall out. We skip a lot of stuff, and you end up getting something like this. So you can see you have your x to the m, and then this other stuff is only 1 over m plus 1, and the 1 over m plus 2, and so on. So it's a power series solution, and obviously it came from, you know, just assuming a power series, and it also alternates signs between each one. Now this looks just like the Bessel function here. And the Bessel function can be written in terms of the summation of this gamma function in the denominator, and also this term involving r over 2 to the m plus 2r. So basic idea is that, you know, you use just kind of like what we talked about before, and you can solve it using a infinite series. And so you can see here that to go from minus m to plus m is basically a difference of minus 1 to the m power, so that if m is even, then this is symmetric. If m is odd, then it's anti-symmetric, going from minus m to plus m. And you can also see that if you add the m minus 1 and the m plus 1 terms together, that this you can put under the summation here and see that that's going to turn the summation eventually into a simpler summation. And so this simpler summation that you get in the end looks just like a Bessel function. And so by doing that, we've discovered a recursion relationship where you can have Jm minus 1 plus Jm plus 1, and the result is a Bessel function. If you look at the difference between the two, you get the derivative of the Bessel function, and you can see all the other recursion relationships that fall out of that. So what that means is, just like with the Legendre polynomial, we got this nice advantage to a Bessel function, and that you can calculate its derivatives without actually having to use something like finite differencing. You can just simply use other values of the Bessel function. And so you can also have these things called half-integer Bessel functions, where instead of having m being an integer, m can be like 1/2 or 3/2 or something. And when you do the half-integer Bessel functions, you can actually get functions of sines and cosines that naturally fall out. And you can see that this comes about essentially going back to this solution to the Bessel function. And when you take the half-integer terms in the gamma function, that's where that'll sum out to. So when you have this, when you use the half-integer terms, there is no relationship between Jm and J minus m, just FYI. And if n is an integer, then the two of them are not independent. They actually have some dependency on each other. And you can also use these Bessel functions, and you can combine them by multiplying by cosine m pi and the Jm and the J minus m in order to get the y Bessel function. And these are always independent solutions. So this is another solution of Bessel's equation, which comes from Bessel's equation. And this makes a lot of sense because if you look at the original equation, since that was a linear equation, then adding together two Bessel solutions should give you a third Bessel solution. Oh, and by the way, this is non-integer, obviously. So what you can get then is that, for example, J1 of x is equal to taking the derivative with respect to x of J naught of x. And this just comes from a recursion relationship. If you integrate this, so you integrate both sides, and you see that the integral of J1 of x is equal to minus J naught of x. And now, when you start putting in extra terms, you could see that if we were going to relate the n term, so we have J sub n multiplied by x sub n, and you take the derivative of the whole thing, that's equal to, from the chain rule, you can see that this is true. And then now we use a recursion relationship between those two, and you can get to x to the n, j to the n minus 1. And so this is consistent with what we see up here between the J1 and the J0 term. And so we can make this other rule, which basically says that we can go from integrating the n minus 1 term times x and getting the n term times x. And then also, you could see that if you do the same thing here, but we put a minus 1 in for the other term, then we get minus x to the minus n, jn plus 1. And so here, it's essentially going, if you look at the two of them, the difference is we have a minus n as opposed to a plus n in the x term. So this is basically just making a statement about the orthogonality relationship between the Bessel functions, which you can use the same way you do with the Legendre polynomials. Now, we also have orthogonality the same way, where if you assume that Jm of kx is equal to f of x, and Jm of Lx is equal to g of x, then both of these are going to satisfy Bessel's equations. And if we multiply the g equation by f of x times f, and you subtract x times g times the f equation, then what you have here is going to be x times f of g prime minus g f prime, and you take the derivative of the whole thing. Then you can see you have this k squared minus l squared term multiplied by the xfg. And so now we integrate both sides of the equation, so we get rid of this derivative. And when we integrate this side of the equation, we're going to have f times g prime minus g times f prime, and then we divide through by k squared minus l squared here. And so this is essentially taking the integral of two Bessel equations multiplied together. So we just plug these Bessel equations back in there, and you can see that you have this relationship between the Bessel equations here. Now, you'll notice here that if if k and l happen to be the same, then you end up with a 0 in the denominator. And you end up with essentially this term and this term being the exact same. So you have a 0 in the numerator. And you can argue that that is non-zero. But if you have k and l different, then what happens here? I mean, is it you're basically going to have the same thing here and here, but all the orders switch. So the question is, are they the same or are they different? Now, the way they resolve this is they said, well, if either the Bessel functions or their derivatives vanish at the boundaries, then the solution to this should be 0 for k not equal to L. And the reason why is because here you're integrating the Bessel functions and then you're evaluating them at their boundaries. And if the Bessel function itself goes to 0 at the boundary, then that means you have a 0 inside of here, and none of the stuff that happens on the right-hand side is relevant. So for k not equal to L, you'd have to have 0. If k were equal to L, then what's the solution? Well, what they can do is we're going to end up using a recursion relationship eventually here. But we could start off by saying that we're going to replace k times x with y. And then you do integration by parts, and you end up having this term involving the y is equal to having the Bessel equation squared times y squared, and then the integral of the Bessel's equation, and then our Bessel function, and then the derivative of the Bessel function. And then once you have this, you can use the recursion relationship here from Bessel's equation and replace one of these Bessel functions with all this other stuff. And so once you've done this replacement, and you can see you have all these derivatives in here, what they did effectively was you had this first term outside of the integration, which is the same as it was before. And then, since this is like a second derivative and a first derivative here, you can basically say that that's equivalent to saying that you have the first derivative, and then you square it and you take a derivative of that. And by the chain rule, you should end up having the second derivative and the first derivative, and you should have, which eliminates a couple of those. And then you could do the same argument with the j prime times jm, where by taking the integral and using the chain rule, you're going to end up with this term involving the 1/2 m squared. So they solve the integral basically by kind of doing the reverse thing. And so now that you've solved the integral, you want to normalize your integral so that when you do, assuming this thing, so this thing is orthogonal because this is non-zero, you normalize your integral so that when you put in the integral, you end up getting a delta function. So if you assume that j vanishes at the boundaries, then when you put in the boundary conditions, this first term is going to disappear, and you're left with the second term involving the derivative. And when you put in, apply the recursion relationship, you're actually going to get the m plus 1 term as opposed to the m term. So what this is saying then is that you have essentially, by doing the integral of these two, you're going to just get back another Bessel function, just evaluated at the boundaries. Now, this proves that the Bessel functions are orthogonal to each other, and since they're orthogonal, then you can use them in as eigenfunctions, and you can actually expand any arbitrary function in terms of Bessel functions, as long as it meets the boundary conditions. So you can say your f of x is equal to some coefficient times your Bessel function, where the Bessel function disappears at the boundary, and then when you take the integral of these two Bessel functions together, then what happens is you get a delta function in the coefficients for n and p, which are these two, and then you have your normalization, the a squared, which comes from the x squared here, over 2, and then the value of the m plus 1 Bessel function at the boundary. And you can use this to solve for your coefficient by just simply dividing, multiplying and integrating the function with the Bessel function, and then dividing through by the normalization factor. And keep in mind that when we're talking about the boundaries here, we're talking about a cylindrical system. So we're talking about, along the axis, not along the axis of the cylinder, but along the radial part of the cylinder. That's what we're talking about. So when we say a boundary, we really mean that circular boundary on the outside normally. So if we have x going from A to B, and so this might be like if you have two concentric cylinders, then you could see that you'll have kx times y mka minus y mkx j mka equals 0 at one of the boundaries. And we've written this so that there's just both Bessel functions are involved, and just as a way of expressing it. Just like with the Legendre polynomials, you have generating functions. And the generating function here, you could see you have f of z and h, and this sum of h to the n, j to the n, z. So it's the same format for a generating function we had before. And you can also take advantage of some recursion relationships in order to see how this works. So if you take your 2m over z, that's a z and that's a 2, by the way, times h to the m over jm, then what happens is, from the recursion relationship, you can see that that's equal to h to the m j m plus 1 and h to the m j m minus 1. And this, in turn, looks a lot like we took our generating function and we took a derivative of it with respect to h, and then multiplied by 2h over z. And so if you did that literally here, you would end up getting 1 over h plus h times f. Just because of the terms that kind of fall out. And so this forms effectively a differential equation with respect to of f, and taking derivatives with respect to h. So you can solve this differential equation, and when you solve the differential equation, this is what you get. So you can see you have a phi of z, which is just some random function of z, which is not defined, and then you have an exponential term, which goes like z over 2h minus 1 over h. Did everybody see where that came from? No, I just solved the differential equation. Yeah, hopefully I didn't miss a sign, but I think that should be right. So what happens then is you can adjust this phi term, since this is really just a extra function, that since it has to be a function of z. You can adjust it so that when you have h to the 0 and or m equals 0, that you get the right answer. And so when you do that, you can see that phi of z is equal to 1. And so your generating function is just this exponential term. And so we could argue that, well, this generating function is just equal to h to the n, a sum of h to the n, and then some u sub n of z, where u sub n of z is not necessarily a Bessel function. And so what they did was they said, well, if you say u0 is j0, so they start off the same way, and this makes sense because of the normalization, then what happens is you can see that all of the recursion relationships should be the same between u sub n and u sub n plus 1 and all their derivatives. And so it may not be a Bessel function, but it has the exact same recursion relationships as a Bessel function. In order to prove it's a Bessel function, you have to take this a step further and you take a derivative of the generating function with respect to z, and you can see that this is going to give you the derivative of the u sub n term, which should equal this analytically, and you can see that the derivative of the u sub n term is going to give you this guy. And now you equate like values of h to the n, and again you get another recursion relationship, which is the same as what you get from the Bessel function. And so you can also see that there are more recursion relationships that pop up. And so if in one of the recursion relationships you'll get clearly shows that if u sub 0 is j sub 0, then that means that j1 is going to be u1 and so on, so this has to be equal to the Bessel function. So we see that there's a certain uniqueness that comes out of this, that only the Bessel function is going to satisfy all the conditions of the recursion relationships which come from the generating function. Now the way you can use the generating function is, first off, you can take your Bessel function of two terms, x plus y added together, and that gives you this solution analytically in the generating function, where you see instead of z you have x plus y. Then, since these are exponentials, you could actually split the exponential, which means that you can actually split it into two generating functions. And from that, you could see that your Bessel function is just equivalent to taking the sum of two different Bessel functions here and multiplying them together, which is interesting. So basically it said if you take your m or your L to be equal to k, and your m to be equal to n minus k, then this works. Salafi also made an integral representation of this, where you could see that he basically did the exact same thing as before, where you take this generating, let's see, he didn't use a generating function. I think he just used the Bessel representation from a few pages ago. Well, anyway, what he did, I think, he must use the generating function here. But what he did was he basically took that and he plugged it into a contour integration, and so that the exponential term here is effectively the exponential term from the generating function. And then he took this t and you set it into e to the I theta, so that you could see that that changes everything here. Because now you've just got a lot of e to the I theta terms which can cancel out. And what you end up with is effectively an exponential of 2 sine of theta minus n theta, or z sine theta minus n theta. And then, since you only care about the real part, this is a cosine of involving a sine wave inside of it. And so that would actually, if it's a simpler representation, although it gets pretty complicated because you have a sine inside of a cosine. But I guess you got to that by just simply using the generating function. And then somehow getting rid of the summation. Now, you can use a generating function. It's kind of a stand-in for the actual Bessel function. And you can see here that this is the generating function where you have the exponentials written. And that's z over 2 on both of these. And here, we don't assume that n is an integer necessarily, or that z is real and positive. And so what happens is this thing goes to 0 as t goes to 0, and that t goes to infinity. And you can see that within each one of these terms that you're going to have at t equals 0, this term is going to blow up, and that term is going to blow up. And as t goes to infinity, you're going to have both of these are going to blow up. So it's going to, essentially, it's just going to be, you don't want this thing to be infinite. So when we use Bessel's equation and you use the integral representation of that, you can re-express the generating function in terms of these derivatives of f of n, where these f of n's are actually Hankel functions of the first and second kind. And these Hankel functions are something that you'll see a lot of in different physics problems, especially like in electrodynamics. And you can see that if you take these Hankel functions and you add them together, then you get this Bessel function. And you have one Hankel function, which is taking the Bessel function, the J Bessel function, and adding I times the Y Bessel function. You have another one, which comes from taking the J Bessel function minus I times the Y Bessel function. And you can see that when you take the differences between these, you can see that the Y Bessel function has to be equal to this. And then, we also define J sub n and J sub minus n. And so all together, these form all linearly independent solutions to Bessel's equation, which are possible. If you take x going to 0, then the Bessel function is supposed to be finite, because if you have this cylindrical problem in the middle of the cylinder, you don't expect things to blow up. And so this is the only finite one where x goes to 0, so that's what you would use in that case. In other words, you're solving this problem where you have like the potential inside of a cylinder, and don't want it to blow up in the middle, so you use the J Bessel function inside. And then on the outside of the cylinder, you might use some other solution. And you notice that as x goes to infinity, this becomes the solution to the different Bessel and Hankel functions, where you could see that J sub n, it goes like cosine, the Y sub n goes like sine, and the Hankel functions go like exponentials with either I or negative I, so they oscillate as well. And then that brings us to spherical Bessel functions, which are essentially, they're Bessel functions, but they have a half integer included with them. And the way that works is, if you have Bessel, you have a problem in cylindrical coordinates, and you have a boundary value problem, then you do your separation of variables, and you know you have boundary conditions where you have a certain radius and a certain height to your cylinder, then you can see that your phi equation is going to depend on sines and cosines. Your z equation is going to be like a hyperbolic term, and your radial equation is going to depend on Bessel functions, where you have one Bessel function which explodes at rho equals 0, and another one which is finite. And so, because you want to deal with a finite solution, you would set d equal to 0. And then you just simply plug in what your potentials are going to be, like your potentials on the boundaries of your cylinder. And once you've done that, you can use that to solve for your coefficients. And then you have a solution which is just the sum of all possible solutions. And you can see here we're using the J Bessel function, and we're using a hyperbolic sign, and then these oscillating terms. Now, also, if you have a solution where at L, Z goes to L, you have a finite potential, which is non-zero, then you could see here that we want to get this final potential at the boundary, so we sum up all of the different modes, all the different n and m values of our solution, and we know that when we end up summing everything up, we're going to end up with something that's a function of just rho and phi, and we solve for what the coefficients a, n, m, and b, n, m have to be. And so we use the orthogonality of the Bessel functions in order to solve for those. And then once we know what those coefficients are, then we're done. So this is just sort of how this would be used in the problem. Okay. I think I talked a little bit last time about the spherical Bessel functions, but that's something where, you know, it's something that pops up if you're talking about spherical coordinates. It's just another complication over what we have to deal with in cylindrical coordinates. All right, so any questions? You know, we've covered a ton of material today.
For the gain functions, going back to the one with 0 to phi, those solutions that came out, they come from this, right?
Yeah.
Okay.
Yeah, I mean, basically, yeah, because what happens is, for example, I have to go way back for this.
Yeah, I think it was half the group.
Yeah, more. I think it was more than that. I think it was somewhere in here when we're talking about Bessel functions and Bessel's equation, and it was right here where you could see that we have the 1 over r effectively, and this is just translating the Legendre polynomials. And so basically, this is the solution, but then this would be the way you express that solution in spherical coordinates. So it is the same thing, and it's still a green function of the Laplace equation. It's just that it's it's written differently.
So in the solution, when they're doing this, so are you evaluating it for some particular L value? Is that like, that's just some coefficient times coefficient?
Yeah. I mean, what you would do is in like E and M, you would decide which L values you have based on what multipolar modes you have. So if you have like just monopoles, just one single charge, then it would be L equals 0. Or if it was a dipole, it would be L equals 1, or and so on. So that would sort of dictate what you're dealing with there. Another question. What? 2. Well, actually, one more. Next week we're going to be doing probability and statistics, and then the week of Thanksgiving we're going to do the review for the final. So we actually only have 2 more lectures. Only one more is going to introduce any new material. And I should say that most students seem to find the probability and statistics the easiest thing we cover in here. Yeah. So yeah, it's not. I mean, the main thing that we really need to know in physics about probability and statistics, especially if you're not like an experimentalist, is probability distribution functions and how they work, and then understanding, statistically, if you make, based on what choices you make, what does that mean, and how do you calculate out and stuff. So there's a lot of ways to illustrate it. Usually I'll use some like playing cards and coins and dice and everything. So everybody bring your money. No. The last problem set is due in December. So it's actually due, it's due on the 3rd because I'm going to be out of town on the 1st. So it's going to be due that Thursday as opposed to that Tuesday like it normally would be. And the reason why it's due on Thursday is because if you would like to get it back to use for studying for your final, I need to get it by that day, and then I can turn around and grade it and hopefully get it to you by like Friday so you can actually use it to study over the weekend. All right, I'll see you guys.